Hello everyone. In the previous video, we went over the Algebra Mastery Exam, and in this video, we're going to be going over the Calculus 1 Mastery Exam. So, if you do not have these 8 lines, remember, you must have them at the beginning of every document, so copy and paste them from the test drive before you start any document, so just have them ready. And remember, when you run this, it will ask you for permission to access your Google Drive, and just say connect to Google Drive and allow. So after that's done, let's jump right into the Calculus 1 Mastery Exam. All right, run properly. So some previously seen commands, these are going to be much less than of the ones that you've seen in the Algebra Mastery Exam. In this case, it would be EQ. Again, we've seen this multiple times. This is going to be an extremely useful one when we want to solve certain things. Let's retry that. All right, run properly. So let's just jump into the previously seen commands. So these are the ones that you've seen in the test right before, and this is just a little reminder. So EQ serves as an equality. So A equals B, then you want to write EQ A comma B, and that's just because the sign doesn't work the exact same way in Python as in like math, the math symbol of equal sign. So keep in mind, this is probably one of the commands that you're going to be seeing a lot from now on. Log refers to the natural logarithm, or ln. So just know that the base for log is always e. Diff is for finding the derivative of a function, which we're going to be focusing on today. So there's two syntax. You can write diff, the expression comma variable, or the object-oriented syntax, which I prefer, which is the expression.diff and inside the variable. So you're welcome to use whichever. I personally like this one better, specifically for diff. We're going to be perhaps using factor, and remember you have factor expression or expression.factor, expand expression, or expression.expand. This two we used in the Algebra Mastery Exam, so you should be more familiarized with them. And then lastly, we're going to be using the idiff. The idiff has a bunch of steps, and it's just specifically for implicit differentiation. So there's one problem that you have to do that you have to implicitly derive. So remember that first we create a function using the function syntax, where we do the dependent variable equals function, and then the dependent variable in the quotation marks, and then outside the independent variable. This is very similar to the syntax that you use for symbols when declaring a symbol, and it has the same idea or the same logic, where you name something, a letter, you make that into a function rather than a letter, and you just have to specify what that function is dependent on. Afterwards, we set the function equal to 0. So we move everything to one side. So in this case, I have this example where we move everything to this side, and then we rewrite the 0 into like expression, or we call it something else. So that anytime we write expression, we actually get this. And lastly, we use the idiff command using idiff, and then the expression, then the dependent variable, and then lastly the independent variable. And this is how you implicitly differentiate. And a little bit of like recap, we might be using trigonometry in certain derivatives. So just know that for trigonometry specifically, it works exactly the same way as in the calculator. All right, new command though. Here is a recall the last computation. So this idea comes from the Python being an object-oriented syntax. All right, so for new commands, so the first one would be recall the last computation. This comes from the idea that Python is an object-oriented programming language, where everything kind of gets saved for a bit and then you can recall it, or you can tell something to do something else with that period. So that period syntax, like an object do an action. So in here, let's say I wanted to recall the last computation. So let's say I wanted to factor this expression and then multiply by 3. So instead of having to do like 3 times factor or something like that, I can just use factor first and then use this little underscore to represent that I'm calling to the previous action done. So 3 times underscore would be 3 times the factorization of C rather than something else. From now on, anytime we write underscore, it is actually referring now to 3 times x minus 1 plus times x plus 1. So if we say, like, for example, expand this expression, we can just write expand, and instead of typing everything down, we can just expand underscore, and that refers back to this. So it would expand 3 times x minus 1 times x plus 1. So this is just a little like shorthand so that so you can do certain work faster. Perhaps you just want to do simple computations or simple like testings between between lines of code. So this would be a nice way of like recalling the previous thing, so you don't have to retype and retype and retype. So yeah, that's what the underscore is for, and we might be using it later on in the calculus mastery exam. So let's start the calculus 1 mastery exam. First, again, I wrote all the variables that I'm going to be using for the exam just at the beginning, just to have them all there, and not having to like retype x equals symbols on every line of code. So find the derivatives of each of the following. Like the name suggests, we're just going to be using diff a lot. So first we wrote the expression down, and then we just find the derivative by saying diff f comma x. Yep. For problem 2, same idea. First, we use s and set that equal to this quantity that I wrote right here, and then diff s comma t. Now notice that we just have this chain of like it did like a chain. So for problem 2, we did the exact same thing. We wrote the expression down and we defined the derivative. I'd actually did the product rule. So notice that you have everything into like little subsections. If we want to expand it, we can just write expand and then the underscore, because it's going to refer to this diff s comma t. Next, to find g, I just do 1 plus, we write the expression down. So 1 plus t squared over t minus t cubed, and then find the derivative of it. And again, we get this, the quotient rule. So because of that, now we have to like factor it to make it like look nicer. So you just factor and then the previous command or the previously done action. Notice that this previous one doesn't necessarily mean this one. And if I were to rerun this, it would actually look at this rather than this diff. So just keep in mind the order that you do things, because now from now on it might matter if you have those underscores. All right, so we call this f equals 10 of 17 plus y. Again, we wrote the expression down. This time I decided to call it capital F rather than just f. And then I did the diff of f comma y, and it gives us this answer. For g, again, we do the expression, and like we've guessed from previous experience, like in here, it's going to do the product rule and some chain rule, and it's just going to leave it into like little sections, and it did that. So we want to expand it into one single expression. So we do expand previous command or previously done action, and there we go. For g, again, write the expression down, do diff of g comma t in this case, and again we get this expression. If we write expand, so let's try that. Expand previous. Let's see if it does anything. It didn't. Doesn't seem so. It just shows that this got factored. Does it simplify? You can ask if it simplifies. And there we go. So if we wanted to have it instead of 2 fractions into 1 fraction, we can actually simplify it. All right, for h is equal to x to the power of cosine of x, we write that down in this expression, and then we find the derivative. So finding the derivative gives us this. Alrighty, so the compute the derivative implicitly. So I actually want to do this step by step with you guys. So first, we have to note that y is dependent on x. So we want to find the dy dx of this expression, and that's probably what you're going to see in your Calculus 1 master exam. So first, we have to say that y is a function. So y is a function, not a variable. And remember that we have to say that it's dependent on another variable, in this case, x. After we write that, we want to move everything to one side. So let's just move the x times sine of y to this other side. So in this case, it would be 0 is equal to y squared minus 4 times x minus x times sine of y. All right, so after we moved everything to the other side, we want to rename this 0 to something else. I'm gonna call it expression or exp1. So let's output a exp1 and see what happens. So did we write this properly? Okay, so minus y sine of y of x. Again, it's already telling us that y is a function. Minus 4x, that's there, plus y squared of x. So in this case, we wrote this expression down properly. Now we can use idef. So idef expression, so exp1, dependent variable, which is y, or the function, and then the independent variable, which is x. And there we have it. This is the derivative or the implicit derivative of this expression. And remember, for the last part, run this math280.export to HTML, and then you should see it in your Google Drive after a couple of loads. Hopefully soon. Doesn't want to load. There it is, Calculus 1 Master Exam. And again, right-click on it, download, and print it. And there we have it. After you print this and submit it to Moodle, you're basically done. So in the next video, we're going to be going over the Calculus 2 Mastery Exam. So until next time, I'll see you around. Bye-bye.